Well, thank you very much. This is Panos Patros. I'm a senior lecturer at the University of Waikato. It's in New Zealand, the other side of the world, I guess, for most of you. And this is a collaborative work with our FuncX friends who invited me to give this talk. Thank you. And also Cardiff University. You can see a long list of people participating in this. So what I'm going to talk today, even though it has like a specific application using FuncX, it's more of a conceptual level. We need to be doing things differently because we're going to be bringing value to communities that are currently underrepresented. And it really continues nicely from what Matt presented. And thank you, Matt, a very exciting talk. And Matt showed the what. I'm going to show the why now, I guess. So what we think is that current techniques and methods that have made certain groups of population and the economy work well for them by benefiting from AI do not necessarily work for some other groups of people. Essentially, the question that we're asking is who should be benefiting from AI? And we're thinking that this needs to be democratized, like more people need to have this kind of benefits. And we identified that the problem really exists in remote and poorly connected regions because it's really tough for these areas to actually connect to the cloud and leverage all of these awesome HPC capabilities that you would normally get. And because existing fields have not really been able to solve this, we are positing that we need a new interdisciplinary field, which we call rural AI. And you can see our definition there. It's the engineering of transformational cyber-physical AI-endowed applications for remote and isolated locations with limited and or unreliable power and networking infrastructure. And I'm reading this verbatim since this is a definition that took us a little bit of time to kind of think about. So what do we mean by rural AI? We essentially mean a concurrent set of requirements that need to be met that are normally not seen as a whole. Each of these sub-requirements that I'm showing you here are normally just tackled independently because it's easier to do so. But what we say is that for rural AI to work, we actually need all of these pieces to be met concurrently. And what we have is we need adaptive AI functionality. So our AI systems need to be able to respond to change. We have the concept of ruggedness and resilience. So this is the point that includes you being in the field. And it's not only that you have bad connection, it's that your system might be in the mud because you're deploying it in a farm. So what kind of problems does this create? We need cooperative federation. One area is not enough. We need multiple areas to be able to get the multiplicative effect of machine learning. We're dealing with big data. And I will be showing you an example soon where we're using hyperspectral cameras that produce 3 gigabytes per second, if I remember correctly. And when you don't have connectivity, you can't handle this. At the same time, the usual concerns of privacy and security are there, but we also have the concept of data sovereignty because in many cases, these are businesses and they don't want to share their IP by putting things on the cloud, or they don't want to be risking putting live video of people as they're working in the forest or in the farm. As you can imagine, we have compute and network heterogeneity, like a variety of different types of equipment are required and a variety of different types of connections, LoRaWAN, 5G, and Raspberry Pis, larger field site servers, robots, you name it. We require power and energy awareness. It's very likely that there's going to be a competition of power and energy between computing devices and the actual devices that need to be operating on a farm. So if you do something that is super energy intensive by using a GPU, then your robot might run out of power. Crucially, we have high human user and human developer barriers that we need to overcome. This is a crucial aspect. If we make a system that it's too complex for a farmer or a forester to use, they're not going to use it. And if we make it also very tough for a developer, no one's going to develop against it. And leaving it last, but it's actually the most important thing, is that all of these things need to be done in a cost-effective way. Some current solutions exist, and they essentially, I've talked to AWS, and they say, oh yeah, we're bringing essentially a mini data center on the farm. Okay, that might work, but it might not be particularly cost-effective. Or some other people have told me that they get huge containers and they fill them up with hard drives because they have collected a shit ton of data, and then they take the truck to the data center with all the drives. Maybe, but maybe this is not a solution that will work for a small farmer somewhere in the Waikato. I also show you a nice graph, I hope, on the right-hand side that kind of exemplifies the things that we discussed for precision agriculture, which is an area that we're focusing on currently. So what we're thinking that will work is a lot around what Matt presented earlier. And what we're thinking is the combination of federated learning and computing continuum implemented on serverless using FuncX is a solution to this problem. So federated learning allows us to be able to train these small models from various stakeholders without sharing their raw data, but with leveraging this shared experience that they have. That way they can keep their privacy and we can create a much better model, but also we don't need to submit through this kind of rugged terrain that has low power, this huge amount of raw data. We do some training locally, we submit the model to a centralized location, it's aggregated, we send it back. And in order to enable this, we require the computing continuum, which, as you know, is a progressively stronger network going from the edge to the cloud, where more and more and stronger computing machines are included. So what we did is we prototyped this idea on a robotic weeds removal application. And the idea is that on pasture, you have weeds, which are essentially plants that you don't want and you want to get rid of them. So what you could do is you can do precision spraying. So you can have your robot going around on the farm and saying, oh, this is a weed, I'm going to spray it. So it just zaps it one by one. The thing is, it might not be necessarily easy to detect what a weed is. And here's the point that cooperative federation starts to make sense. If all of these farm owners pool their resources together, they will be able to get a better model on what it means to be a weed, and also make it adaptive, because with climate change, things change, for example. The model that you had in the past will not work. So what we're looking here is a robot and hyperspectral camera system. I'm putting the design specs over there, but this is essentially creating a data rate of 9 gigabytes per second. And the reason for this is that hyperspectral cameras do not use three numbers per pixel, RGB. They use 120 bands, hence they're hyperspectral. This creates a number of trade-offs, global versus local information, power, consumption resources, and performance versus fault tolerance. And essentially, the solution to this would be federated learning with computing continuum. This is what we think. So we did a proof of concept with FuncX. We set up a small set of clusters. We had 3 locations that were representing images taken from 3 different sites. There were lots of variations between them. We deployed them on edge clusters represented by 4 VMs each, and we also had a federation server. Everything was orchestrated with FuncX, and it was essentially allow us to overcome the barrier of human developer by providing a nice and modular application and ease of development, you know, all the good things that FAST provides. So on the right-hand side, what you're seeing on the very top is what if you had all the data and you could create a centralized model. You would do awesome, great, but it would be very cost ineffective, or it may be not even feasibly possible to transfer all of the raw data from the farm to the cloud. However, the next 3 that you're seeing is how well the federated models did, and they did spectacularly well, if you see. And we tried a variety of failing rates to simulate bad rural conditions, and you can see that even with 75% failure rate, we reached essentially an accuracy of 80%, which is a very good result when you compare it with the other 3, which is just using local only information, which drops dramatically. So federated learning seems to work great. It meets all these requirements that we need on top of the computing continuum. FuncX did a great work, so thank you very much for providing this platform. So what on from now? We're in the process. So I'm presenting you essentially a summary of a paper that we've just submitted. It hasn't been accepted yet, so you're getting an initial nice preview of it. What we're seeing is a variety of challenges that essentially this new rural AI field had that go along the various fields that we've been merging together, like the IoT, AI, and computing continuum, which is essentially the area of autonomics and serverless that Matt discussed earlier. We're also in the process of applying some grant funding, so fingers crossed that this will work well. And I think that is all that I will have to say for now. So thank you very much. Any questions?
Awesome. Thank you, Panos. Any questions?
Hey, Panos, I have a quick question. Could you go to the previous slide? Between the clusters, what sort of bandwidth do you expect?
So that really depends on the availability on the rural communications. Sometimes we're at the very low level of maybe few kilobytes per second, depending on how badly they're connected, with also intermittent failures.
I see. So did you consider like how, if say one cluster is running really slow, how that would affect the overall training speed and stuff?
Yes, this is something that we have identified as future work, essentially the various synchronization effects that would be required. So for the time being, we just simulated by throwing random failure rates on the packets arriving.
I see. Okay.
Yes, Matt.
Yeah, no, I'm wondering, I was thinking with that cool slide with the car that goes around and sprays weeds, doing something even more distributed, if you've thought like having ground stations for weeds, so like a non-mobile platform, because you could imagine with some crops driving around either isn't feasible or isn't ideal, and then having another resource like a vehicle or maybe even a drone that makes decisions based on those stationary endpoints, and whether or not you think that could be a possibility, or
yes,
if it needs to kind of be this roving.
This is definitely a possibility, and this is part of the things that we're considering writing up now in the grant application. And I think, given your association and the relevance that your project has, it might be worthwhile considering including you.
Sure, no, that'd be really cool. Thank you.
Essentially, we need money to do what you said. We don't have it for the time being. But yeah, we're envisioning a complete computing continuum where the robots will be doing some of the computation, like FuncX will be running on the robots. Then we'll have field side units. So I can bring you back to this. There's going to be field side servers. And we've also talked with local wireless ISP providers that will be able to help us communicate. And we can also set up some beefier compute on their wireless repeaters and go all the way up until we reach the cloud. So each of these stations will be able to do more and more things. So there's going to be lots of things to essentially to answer, where you're going to find your 1,000 endpoints. I'll give them to you.
That sounds terrific. Awesome. Yeah. Very exciting.